Okay, so in this lesson I want to look at finding particular solutions to differential equations. Okay, particular solutions to differential equations. Okay, remember a differential equation is just an equation containing derivatives. The definition of a derivative, dy dx, is equal to the limit as delta x approaches 0 of delta y over delta x. Delta y over delta x is just our definition of slope. So this is, dy dx means the slope as the horizontal change is almost 0 or tends towards 0. Each derivative has two differentials. They are called just dy and dx. And dy dx is just a ratio. It's just a fraction. It can be treated as such, so don't forget that. I'm going to look at finding particular solutions. Just a quick reminder on finding a general solution. Suppose I want to find the general solution to this, dy dx equals 6. The general solution includes the constant of integration. So if dy dx equals 6, what I'm going to do is see if I can separate this. And the equation is separable if I can gather all my x terms on one side with the x differential and all my y terms on the other side with the y differential. And that's very easily done here. I just multiply on both sides by dx to find dy is equal to 6x times dx. So dy is equal to 6x times dx. I've separated. My next step is to integrate. I'm just going to take antiderivatives. Notice I'm factoring the 6 out from the integrand in one kind of step. And I've got to know how to take antiderivatives. The antiderivative, again, there's a 1 hidden in here of 1 with respect to y. We generally leave it out, but that's just the antiderivative of 1 with respect to y, which is y. On the right hand side, it's going to be 6 times the antiderivative of x, the power rule. Add 1 to the old exponent. The old exponent is 1. Add 1 to that, you get 2. Divide by the new exponent, 2. And add the constant of integration, I should say. So we get y is equal to 6 divided by 2, which is 3. X squared plus c. That is my general solution. So it's a general solution. And it's a general solution because it contains the constant of integration. There are infinitely many possible values for c here, and that would make this true. What's new in this class, what we're going to develop that is going to look at finding a particular solution. So we're asked to find a particular solution given the following conditions on the variables here. So y has to equal to 15 when x is 2, and there's my differential equation, dy dx equals 6x. So we just do the same thing. All we do first of all is to find the general solution. And remember, we've just gone through this, so I'll just write it out straight away. We just went through this solution here. We solved this and we found that y was equal to 3x squared plus the constant of integration. But in this case, we're given a condition on the variable, and the condition is that y has to equal to 15 when x is equal to 2. So we know that y is equal to 3x squared plus c, and we know that y has to equal to 15 when x equals 2. So using substitution, substituting 15 in for y and 2 in here for x, we can deduce that 15 must equal to 3 times 2 squared plus c in this case. In this particular case, 15 has to equal to 12 plus c. So solving here for c, you'll see that c has to equal to 3. Okay, therefore, my particular solution in this case is that y is equal to, remember we said y has to equal to 3x squared plus some constant. And in this particular case, given that y is 15 when x is 2, the constant is 3. So that's called the particular solution for the differential equation. Y is equal to 3x squared plus 3. So in general, if dy dx is equal to 6x, then y is equal to 3x squared plus some constant. In this particular case, that y has to be 15 when x is 2, while y has to equal to 3x squared plus 3. Okay? So it satisfies the 3x squared plus c, and it also satisfies the fact that y will be 15 when x is 2. Okay? So we can use those general solutions to find particular solutions. Here's another example. No. Actually, I'll go through another example in the next video.